Today we're going to go ahead and explore the existics equations naked. That's right, we're not going to get into existics or temporal mechanics at all. We're just going to go over the equations, their unique features, and why I think they're actually the lost equations. Now, why do I say this? The reason why is when you actually play with the existics equations mathematically, there's a lot of interesting overlaps with Pythagorean mathematical concepts, such as the Pythagorean triples, the Pythagorean theorem, etc. In fact, I would argue that the existics equations can actually act as an alternative to the Pythagorean theorem in specific circumstances. So, we're going to go ahead and let A be greater than B. Okay? And A over B, we're going to let that equal N. And B over A, we're going to let that equal U, where U times N equals 1. Now, this is just basically a definition of a reciprocal relationship between two values. But this is where the existics equations stem. What the significant difference is with the existics equations, what we do is we create two continued fractions, but the continued fractions carried out in the numerator rather than the denominator. So, for instance, A over B plus A over B plus A over B to, infinitely carried out, that equals N star. And then, of course, B over A minus B over A minus B over A, so on and so forth, gives us U star.
Great.
Now, when I first started playing with these, one of the major concerns was, do these converge or do they diverge, right? And so what we'll do is, let's go ahead and convert the continued fraction over into a series and look at it from a series perspective to further that point. So for N equals A over B. We'll let that be N naught, or the initial N. And 1 would be A over B plus A over B. And 2 would be A over B plus A over B plus A over B. And then N3, of course, would be A over B plus A over B plus A over B plus A over B. So if we wanted to solve for N star, what we could do is we could take the initial N naught, and we're going to subtract this from that so that we're just left with this little part here. So what we do is N naught plus N1 minus N naught. Okay?
Yep.
And then same thing down here. If we subtract N1 from N2, we're basically getting rid of this and having that. So basically what we're doing is we're just taking the little smidgets off of the end of each as we continue down this, and we're just adding those up, those little infinitesimal amounts.
Sure.
So the way that would look would be N star equals N naught plus N1 minus N naught plus N2 minus N1 plus so on and so forth. With U, it's basically, so for U, we have B over A equals U initial, B over A minus B over A equals U1, B over A minus B over A minus B over A equals U2, so on and so forth. In a very similar manner, we would be removing that from here and just bringing this in, but because there's a minus sign, the equation could be done two different ways, and I'll go ahead and show that.
Sure.
So I'll go ahead and I'm going to rewrite the n star equals n naught plus n1 minus n naught plus n2 minus n1 plus dot dot dot. And for u, the way it looks is u star equals u naught plus u naught minus u1 plus u1 minus u2 plus so on and so forth. And depending on how you do it, this is either a plus sign in here and that's a minus sign and those are reversed, or vice versa. So this is where, the real question is, do these converge? Or are they divergent, right? So let's go back and look at the continued fraction version of this, and there's actually a pretty neat little trick. So let's look at n star for starters. So a over b plus a over b plus a over b to infinity, right?
Yep.
That equals n star. Well, what's kind of interesting is because this is an infinite series, like you can think about the hotel paradox,
Yep.
where there's infinite rooms.
Hilbert's Hotel.
Hilbert's Hotel, and we move everybody over one room, but there's still infinite numbers of rooms,
Sure.
right? So if you think about it, this little section up here, that can be set equal to n star. So what we do is we just have a plus n star over b equals n star. Now what's neat about that is I can just move the b over like this, and then I can also move the n star over, so what I end up with is a equals n star times b minus n star. And I can, of course, factor out the n star. A equals n star times b minus 1. And then, of course, a over b minus 1 equals n star. So, of course, when you see this, we know that as long as b is greater than 1, n star can converge, right? So let's go ahead and work out the same thing for u star. So b over a minus b over a minus b over a minus b over a, so on and so forth, equals u star. And again, that can be set equal to u. So we get b over a equals, minus u star equals u star. Then we get b minus u star equals u star times a. We can bring the u star over and get b equals u star times a plus u star. Factor out the u star, which gives us u star times a plus 1. We can bring that over and get our b over a plus 1 equals u star. So u star clearly converges. All right, so now let's go ahead and solve for a star and b star now that we have u star. And as a reminder, we started with our conventional reciprocal relationships, right?
Yes.
So since we solved for n star and u star, we now need to solve for a star and b star. So we'll go ahead and just reuse this sheet right here. A star equals a plus n star minus I. And then b star equals b minus I minus U star. And so what's really interesting about when we solve for A star and B star, we get this interesting little equation here. And so what we end up with, anytime we have A over B, that always equals N star minus I over I minus U star. So I'll go ahead and graph this to give an example.
Great.
So we're going to go ahead and make a little graph here. And these units correspond to A, and these units correspond to B. So let's say we have some point right here, and this point is B. And then because we subtract this quantity from B to get B star is going to be slightly behind B, somewhere right here. And so here's B star. So that's B star going to B. And then right here, this would be A. And then we'd be going up this amount to here, which is A star. And that's like this. So we get this nice little triangle where this length equals N star minus I, and this length equals I minus U star. So the fact that these ratios are equivalent indicates that that's a 90-degree triangle. And so once you realize that's a 90-degree triangle and you see the simplicity of this, the first thing, well, at least for me, that came to my mind is, okay, one way we could test the equation is by applying the Pythagorean theorem.
Sure.
Right? Okay, so let's go ahead and do that. But for A and B, we'll use 3 and 4 from our famous 3, 4, 5 triangle. So we're going to go ahead and apply the Pythagorean theorem.
Sure.
So we'll go ahead and let A equal 4 and B equal 3 for our proverbial 3, 4, 5 triangle. So A over B, we need to find N star and U star. Okay. So N star was A over B minus 1. U star was B over A plus 1. And in this case, we get 4 over 2, which equals 2. And in this case, we get 3 over 5, which 3/5 was
0.6.
0.6. Okay. So now, something I forgot to mention was solving for I. Remember, U times N equaled 1, primarily because U and N are reciprocal numbers, right? So we need to, then we need to solve for a similar type thing, but we're going to call it I, the identity constant, where basically I is greater than 1 for all values where A is greater than B. But if A and B are the same, then I would equal 1. Hence, identity constant.
Sure.
Right? Okay. So, to solve for I, we need to multiply 2 times 0.6. And what that gives us is 1.2. Okay. So, now we're going to apply the Pythagorean theorem. So N star minus I squared plus I minus U star squared equals some value squared. Okay? So N star minus I, what's N star? It's 2. What's I? 1.2, so 2 minus 1.2, quantity squared plus, it's I, 1.2 minus 0.6, quantity squared equals, so this turns out to being 0.8, right?
Yes.
Squared plus, and this turns out to being 0.6 squared equals. All right, Matt, so what's 0.8 squared? 0.64?
0.64.
0.64. And 0.6 squared is 0.36.
0.36.
0.36. And that equals 1. Now, when I first saw this, the first thing I wanted to do was, can I apply this to unit circle? Because that would be really fun. But what I ended up finding out is if I come in here and apply the different Pythagorean triples, what ends up happening is this number always gives me the index of which triple that is. So for instance, the 3, 4, 5 triangle is the first of the Pythagorean triples. What's the next Pythagorean triple? The 5, 12, 13 triangle. Okay? So we'll go ahead and let A equal 12 and B, here we're going to let A equal 12 and B equal 5. So 12 over 5, we're going to solve for N star and U star. So 12 over 4 is 3. And 5 over 13 is?
0.3846. So whatever decimal you want to take it to.
Okay, 0.3846 it is. All right. So now, what's 3 times 0.3846 so we can solve for I?
That's 1.1538.
Okay. So 3 minus 1.1538 is
1.8417.
1.847.
1.8417.
Okay. And then so then we need to now do 1.1538 minus 0.3846.
3846 should be 0.7692.
Okay, so what's 0.7692 squared?
0.5916.
0.5916.
Correct.
And then what's 1.8417 squared?
3.3918.
Okay, so what's 3.3918 plus 0.5916?
3.9834.
Which obviously is approximately 4.
Correct.
Which, if we square root that, gives us 2. So as the first set of Pythagorean triples gave us 1, the second set gave us 2. All right, and it just keeps going. Now, here's the really cool thing, Matt. It turns out that in the 3, 4, 5 triangle, if you draw a circle inside the triangle that touches all 3 sides, but just by 1 point, right? It has an area of pi. Reason being is that the radius of the circle is 1. So this is actually giving us the radius of the circle that's embedded within each of these triangles. So, not shocking, the Pythagorean triple triangle has a unit 2 with its embedded circle, so on and so forth. So this is the reason to me why these equations seem to be something that has been lost. I would venture to argue that Pythagoras or the Pythagoreans or some ancient Greek mathematicians probably did have these equations. That's my argument. Because I have a hard time thinking I'm the first person to stumble across these since man's been playing with math.
Maybe rediscovered.
Yeah,
Maybe not
rediscovered,
invented, right?
Yeah, exactly. I think I'm willing to go with that. All right, so now that we've gone over the some of the interesting aspects of the existics equations, what's next on the list?
So we've covered so many of these. We already talked about the Pythagorean triples, going back to summation, about Easter eggs and the fine structure constant.
Okay, so
Always a hot topic.
yes, this all started with a series with two very unique continued fractions, where the continued fractions happens in the numerator rather than the denominator. And those, of course, can be delineated into a series. I think I have a page, yep. And so here's this series. So the question was, of course, do these converge, right? And we found that they do. But here's something I want to draw your attention to. What n star and u star actually represent is this little extra numerical attribute that can maintain right angles, right? So for instance, with the 3, 4, 5 triangle, we already know the 3, 4, 5 triangle is a right angle, but if we apply the existics equations, even the slight offset for A and B still maintains a right triangle, and it has to do with that little amount, the n star minus I, or the I minus u star. So let's isolate those values and just have n star minus n equals significant amount, and the u minus u star is also a significant amount, right? Okay. Now, the reason why I say this is an Easter egg is in all my existics stuff, my Existics 101 PDF, which you can get on existics101.com, or just search Gavin Wince Existics PDF. I'll probably put it as a link in the description.
Great.
But everyone will see that my proverbial example is where I have A over B equaling 100 over 20. Okay? Well, let's revisit this and dive into this significant amount.
Right.
Okay? Now, let me ask you this, Matt. Would it be odd if somehow I ran out of paper? No, I'm just kidding.
Heading that way.
Yeah, right? Would it be odd to you if I could just whip out the fine structure constant with these equations?
Yes.
Why?
Well, that's a fairly significant number when we talk about mathematics or analysis, and just to whip it out of thin air is, pretty impressive.
What's the significance of the fine structure constant in physics?
Well, we tend to see it in a lot of different measurements. It's unitless, and for some reason, this number pops up through many different facets of physics without real explanation.
And it's basically a number that allows the mathematics to be consistent with observation,
That's
right?
correct, yes.
And a lot of physicists have, Richard Feynman spoke about it, Paul Dirac, many have spoken about the mysterious 137. So how appropriate that some lost mysterious equation from time immemorial may actually derive the fine structure constant. So let's have a whack at it, right?
Might be dangerous. Let's do it.
Yeah. Okay. So we're going to go ahead and start with, we're going to let A equal 100 and B equal 20. Okay? Now, going through all the math to save some time, Matt, what do I have for n star?
N star equals 5.26315,789.
Okay. And then what does u star equal?
U star is 0.19801,980.
Okay. And to maintain mathematical consistency, I'm going to try my best to stick with 8 digits.
Okay.
So there's a 0 at the 8th digit, so it is what it is.
Sure.
But there's a reason why I'm using these particular numbers, obviously. Okay, so remember that little significant amount.
Yes.
What I find interesting about the fine structure constant is that it's basically 1 divided by 137. However, that's an approximation.
Right.
And for me, the significance isn't so much the 137 aspect, because that just looks like some kind of number that would pop up in geometrical mathematics or something that has to do with the underlying nature of the units we use and the equations we use. So that number's not strange to me. It's a prime number, whatever. It's the 33rd prime. 33, right? Maybe that's it. What's significant to me is the decimal number that extends from that, the 0.35 yada yada.
Yes.
That's the significant part to me. So that's why I want to go back to the significant part of these equations, where we're basically going to examine n star minus n, right, over u minus u star. And so do you have a number for me on there?
So that would be...
Let's not forget I.
Yeah, I was going to say, we got to do I. So I is 1.042 20948.
Okay.
Now, n star minus n naught
is
5 point... Well, if we take
subtract
it out here, we're going to subtract the 5. We want to do that. So we want 5.26315,789 minus 5.
Is 0.26315,789.
That's correct.
Okay, and what's the u minus u star?
U minus u star equals... you want the final number?
The final number.
Final number is 0.0019802.
Okay. So, when I divide those numbers, what do I get?
That's where you get 132.894,601.55.
So right out of the gate, this suspiciously is looking way too close to the fine structure constant. And the reason why I'm going to say this is because I already know that n star equals 5.26, and I plug that in there. That almost gives me the 137. So this is why I'm going to go ahead and push this a little further.
Sure.
Right? And obviously I did some tinkering. So what I end up with is n star minus n over u minus u star quantity plus, right, plus
Yes.
n star minus I squared. So what's the next value you have written there?
So next value is, we have the 4.17.
Okay, so n star minus I, what's that turn out to be?
So we have 4.1769573.
Okay. And then we already know that this is the 132.894,60155. And then we add those, and what we end up with?
We have 137.071 55885.
All right. Now, we're like so close. But what's crazy is that the fine structure constant's 137.035, and I'm looking at that 0.71. That's almost twice. So you know what I'm going to do? I'm going to do some mathemagic. I'm going to go ahead and let's just call this. We'll call this 1 over alpha star.
Okay.
Okay, so 1 over alpha star.
Okay.
So we're going to take 1 over alpha star. Alpha star. And we're going to subtract from it 137. And we're going to divide that whole quantity by 2. And what do I get?
137.035.
Oh, wait. No, that's if I add. I subtract this. So do I have...
So you have alpha minus...
Yep. It's 1 over alpha star minus 1 over alpha minus 137 divided by 2.
That's correct.
And what do I get?
That's 137.035 779425.
Now, it's pretty darn close.
Pretty close.
But something stood out to me, and that is that this particular expression of it is off by 0.00022 because in the fine structure constant, those would be 9s. And what I find really interesting about this particular number is it shows up as an error correction in the unitary triangle of the CKM matrix. That's quite the thing to kind of stumble upon on my path to the fine structure constant.
What a coincidence.
What a coincidence. However, who knows? I'm just noticing. Math is funny. You tend to notice patterns in mathematics, whether the pattern has any significance or not.
Maybe you got lucky.
Yeah, I just want to draw that out. But here's where things get interesting. If I divide 1 by this number, what do I get?
0.00729 736426.
And what's the actual experimental?
Experimental fine structure constant is 0.00729 735 257.
So, where they're different is here. So I've got 1, 2, 3, 4, 5, 6, 7, 8 to the 8th decimal point, the fine structure constant.
Pretty good.
That's pretty darn
Pretty good.
But it's not good enough. Because again, certain numbers stick out. So let's just go ahead and ignore some of the excess off of here because at this point, we're just keeping track of where it diverges. When I subtract these two numbers, what do I get?
0.000000012.
So 1, 2, 3, 4, 5, 6, 7, 8. So 7, 8, basically 1.2, which equals 1.2 times 10 to the 8th. Now, I'm a tricky bastard, okay? Because you know what's really weird? What happens if I divide this number by 20, which just so happens to be the B that we started with, so I'm not veering into... I'm actually circling back to how these numbers actually have some significance. So what happens when I divide this number by 20, what do I get? I get 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 6. Now, what is so significant about 6 times 10 to the minus 10? That's actually the value of the ratio of baryons to photons in the observable universe. So not only did we get the fine structure constant, but when we subtract the experimental value for the fine structure constant and divide that by 20, or B in this case, we get the value for the ratio between baryonic matter and photons in the universe, which is a mysterious number because this has to do with the asymmetry between matter and antimatter. Well, it looks like the asymmetry between matter and antimatter has something to do with what we're looking at here. So this would basically literally be baryon-photon ratio, right?
Yes.
So the fine structure constant we got from existics minus the fine structure constant we get from experiment divided by 20 gives us, or B I should say, but fair enough, gives us the ratio between baryon and photons in the universe, which equals about 6 times 10 to the minus 10. Right?
Yes.
Okay. But there's more. If we take the baryons over photons, right, and we multiply that by A and divide that by the fine structure constant we got from the existics equations minus the fine structure constant, what we end up with is 5, which is the ratio between A and B, the very equation we started with.
Yes.
But you know what's really crazy about 5? That's the percentage of visible matter in the known universe. So we got the percentage of the visible matter in the known universe, the baryon to photon ratio, and the fine structure constant, all from just playing around with the existics equations.
Pretty interesting.